Hi, this is Gina and Menzi.
Hi, this is Jackson Clary.
I'm Rehan Syed.
And this is Julian Zhang, and we implemented the Simon block cipher on FPGA.
Okay, so here's our FPGA board, and the bottom right switch here shows whether the FPGA is in encryption or decryption mode, with the LED above also indicating such. When you flip the switch up, this means that it is in encryption mode and the LED lights up, and when you flip it back down, this is in decryption mode. So when the computer sends data via UART to the FPGA, this TX LED will light up for an instant, and then this 7-segment display here, which shows our FIFO, which will be explained a little later, will also flicker to show that it has filled up, and then once it fills up, it instantly lets go of all the data and passes it to the cipher. And once the cipher completes its operation and sends the data back to the computer, this RX light will light up for an instant, and the data has been received by the computer. To interface with the Nexus A7 board, we're using a computer running a Python script that sends and transmits data via UART, and both of which will be explained later.
All right, welcome to our project demonstration. We're going to be showing off the encryption and decryption process for these generously provided NSA examples, as well as a couple that we have made ourselves. On the right, you'll notice a few things such as the key, the plaintext, and the ciphertext. We are going to be going through all of these using the terminal here, which is shown on the left, and the sources are here to prove that we are actually encrypting and decrypting and not just making things up. After running the program here on the left, we are going to be asked to input the key, and then immediately picked for a hex or ASCII. So first we're going to be inputting hex, and now I'm going to have to be inputting 32 bits of data. Now our program is capable of running 32 digits of hex. The cipher on this side is only 16, so we're going to be adding 16 characters of gibberish at the end. Now after running, what you'll notice is that this output here, the first half of it, is identical to the ciphertext provided by the NSA. Now, if I were to run this program again and flick this button to swap it back into the other mode, and I pick the same key, you'll notice the output will be identical to the original input, which is shown right here. After running, you'll notice that this hex output is identical to the original hex input. We're going to run through one more example. For this section, we're going to be going through some plaintext and keys that we made ourselves, as you can tell by their lack of creativity and their sincerity. On the left here, just as before, we can run this module, and for this, we're going to be demonstrating the maximum bandwidth, which is 16 ASCII characters, as well as obviously demonstrating the capability of this to input and output ASCII just as much as it could hex in the previous module. And as you can see, the ASCII message has been decoded to show the next message.
Here's the block diagram for our project. This may serve as a useful visual reference for the following code review portion of our demo video.
So this is our UART module, which will allow for communication between the FPGA and the host computer. And this is our top module, which instantiates the complete UART core. And the UART core essentially has many sub-modules that will allow for this communication to be possible. The first of which being the baud rate generator, which is essentially an extreme clock divider that allows for a maximum bits of 9600, which is our baud, and that is the baud that the Nexus Arctic 7 works with. And then there is the receiver module, which essentially takes in the serial data and turns it into 8 bits of binary that we can work with. And these two modules we borrowed code SIMON64 from FPGA Dude on YouTube. You can see the source at the top on our GitHub. And then we have our FIFO RX module, which was the hardest part of the code to implement for us. So we had many ideas that we had to scrap as we kept trying things, and eventually this was the design that finally worked for us. So the way the FIFO RX module works is that there are 32 blocks of memory, and each block of memory can hold 8 bits, and essentially it collects these 8 bits from the receiver module one by one until all 32 blocks are filled up. And then it sends out all these 32 addresses as 256 bits of data out to the next step of this communication process. And essentially the way this works is that there is a current write address and a next write address, where next write address is always current write address plus 1. And the current write address starts at 0, and every time 8 bits of data are written into one of the addresses, it increments by 1, and then once that increment reaches 32, that means that the FIFO is now full, and now it will be marked as full. And once the FIFO is full, there will be a functional reset, and it will now be marked as empty, because immediately we will empty this FIFO and send it to the next step, and these 32 blocks of data will be sent out. So as you can see over here, the data is read out, and it's actually an output into the top module. And over here, here's our 256 bits of data. And the first 96 bits are the key, the next 64 bits are the first block to be encrypted, and the second 64 bits are the next block to be encrypted. And down here, the encryption actually occurs, which Jilin will talk about. However, after the 2 blocks are encrypted, encrypt out and encrypt out 2 are then outputted and then sent back into the UART module as write data. And this data that I just mentioned, these 128 bits, are taken in to the FIFO TX unit. And the FIFO TX unit works in a very similar manner to the FIFO RX unit, in which that it collects all the data at once and then spits it out 8 bits at a time. So it's essentially the FIFO RX unit, except in the opposite direction. And this logic was created in a similar manner to our FIFO RX unit, and the design worked for both of them, thankfully. And here the data is all written out, and it uses the same incrementing process with current and next address. And after the exits the TX unit, it enters the transmitter module, which we also borrowed the code for. And this transmitter module essentially takes in these 8 bits of data one by one and sends it back to the host computer as serial data. And one last thing to mention is that we keep track of what's going on with this 7-segment display. And this 7-segment display essentially shows us when the buffer is full or empty. And since we have it empty as soon as it is full, it will flicker for a very brief second.
The SIMON family of block ciphers is based on a FISO cipher structure comprised of a key scheduling function and round function. For our project, we implemented a specific configuration of SIMON6496, which means we receive input block size of 64 bits and key sizes of 96 bits. And what you're seeing here is the key scheduling, or you can also think of it as the key generation function. In the generation of a new round key, 2 constant sequences are being used, the first being 2 to the power of the word size, which is half of the block size, so in this case 32 bits. The second is a configuration-specific constant sequence Z, which is 62 bits. You also use 2 previously generated round keys, and all these inputs are used in a series of bitwise operations to generate a new round key. Here's a graphical representation of the key scheduling and the associated key scheduling equation. Notice that it's dependent on the number of keywords M, which is also configuration specific. And in this SIMON6496 cipher, there are 3 keywords, so M equals 3. For the round function, both of the encrypt round and decrypt round modules are implementations of the round function with slight alterations in which halves of the blocks are being operated on. To produce the block used in the next round, a block and round key are taken in as inputs, and the block is split into halves known as words, and used in another series of bitwise operations, including an XOR with the round key. And note that if we are at the final round, the block is the actual output of the cipher. And finally, to hook everything up, here is the SIMON6496 module, which generates all of the round keys. Note that the first 3 are just slices of the user inputted key, and it performs all rounds of the encryption and decryption using the unique round keys. In our configuration, 42 rounds are performed. Finally, a mux is used to choose between the encryption or decryption result based on the setting the user has on the rightmost switch on the Nexus A7 board. To verify our results in simulation, we implemented a test bench based off of the test cases cited by the NSA's work on SIMON. And as you can see, our outputs match the expected output given the message, key, and the selected encryption or decryption mode. So here we have a input, the key, and then this is our expected output. And if you take a look over here on the simulation, we see that this result is the first result we see. And then we are decrypting that same message, so the next one appears the same. And if you keep going for the rest of the test cases, they all match the expected output. So our cipher is correct.
So here we have our UART Python code. This code is designed to interact with an FPGA through a serial connection, allowing the user to send key and data information for encryption and decryption. The code also measures and prints the time elapsed during the communication process. So as we can see here, promotes the user for 1 for encryption, 0 for decryption, and promote the user for the key, and also makes the user to choose between ASCII or hexi, and then enter the data for that, and then starts recording the elapsed time, and then after it reads the data, it prints the elapsed time.